thank you for coming. My name is Steve Kushman. I am the former president and present director and project manager here at Radio Central CHRS. Thank you all for coming today. You know, it's Radio Central. We're the California Historical Radio Society, but we're all about modern communications, and television is just another spoke in that big communications wheel. And we are really glad that Tom has organized this group and brought it here to celebrate television in this place. Tiny bit of background, I shouldn't do this probably, but I was in television for 50 years, 3 years at KEMO Channel 20, and 47 years at KGO TV. So this is not unfamiliar to me, and I'm really so glad that we are celebrating TV. So without further ado, Tom Albrecht.
Okay, greetings everyone. Welcome. Nice turnout today. Great to see so many people interested in antique technology. And it's not just the equipment, it's also the people. We celebrate here antique TV technology. You know, what a big impact on society it was. Think of how many hours countless people spent in front of the boob tube. So we've got wonderful artifacts like this camera you'll hear much more about today. There's also some wonderful sets on the back tables back there. When we do our introductions, people will have a chance to talk about some of those as well. But it's not just the equipment, it's also the people. Some of you here are a direct part of that history of what television was and what it has become. We already heard that Steve spent 47 years at KGO. That's a good long run.
Yeah.
Fantastic.
It was. I was in videotape operations, they called it, and then went into editing, and I edited on everything from 2-inch videotape all the way down to 1 inch to 3/4 to 1/2 inch, and then to the computer, to a mouse. Yep. And when you can look at, my deal is, if in those days a half-hour's program would be on a reel about this big and weigh almost 20 pounds, now everything is this big and it's in your pocket.
Sure. Did you bring that splicing machine?
I did. The splicing machine is right back there on the table.
Yep, good. I see the microscope. That's probably part of it. So, yeah. So anyway, Steve has started our introductions for us. We'll spend maybe as much as a half hour here this morning passing around the microphone. I want to get to know who you are. Some of this is old hat. Many of you have been here many times, but there are new faces as well, so please take the time to say again who you are. But also be sure to mention if you're one of these people who played a direct role in what television has been over the years. We want to hear about that. And if you did bring a set or two or any other equipment that's on the back table, feel free to mention a word or two about that when your turn comes up. So we're going to start right here.
I'm speechless. I'm Jimmy Fink. Been a member here about 11 years. Lived just down the street, so it's very convenient for me. So if there's a running, leaky faucet, I'm the first one they call. The plugged-up toilets are not as fun, though. But anyhow, so I'm a retired electronic engineer, and I've been fiddling with video and TV ever since I think about the 6th grade. I was in the school library with my homeroom, and they had all these books on scanning disc televisions, and that kind of got my eye. And I actually built a camera, which never worked right, and a receiver, which, you know, had 2 erector sets, identical motors. I figured, well, they'd spin about the same speed. I didn't know about synchronizing, so I'd have to put my hand on the shaft and slow it down. But anyhow, that was a fun project, and then I got into a little more involved with, I built a color camera out of 2 old black and whites, put them in a thing and adjusted, put lenses on them, filters, and built an NTSC encoder on a proto board with a bunch of ICs and stuff. And that was fun work. We were using a cartridge vision, those old machines that were out in the early 70s that were half-inch tape on a cassette. They would go in there. The reels were stacked on top of one another. I ran those in the ground. But anyhow, so then I retired, and I've been retired longer than I have worked. So anyhow, it's fun to come here and keep my foot in the door and work on projects, whatever they are, and it's kind of enlightening, and it's convenient. It keeps my interest perked up.
Hi, my name is Fred Deal, and I have been interested in all kinds of mechanical and electronic things probably ever since I was 5 or 6 years old. And my first television I was interested in was 1959. I saw the real McCoys. They had this Hallicrafters T-54, and I wanted it, but only found 20 years later I found one in the late 70s and recapped it and got it working. And I also I'm into collecting antique phonographs and early radios and wire recorders and early tape recorders, stuff like that. And so I have been a CHRS member since 1982. We started in Sacramento at the library in North Sacramento. We had our meetings, our main meeting, swap meet once a year there, and found a few artifacts there, and just I do repair and wind up phonographs and early televisions and antique radios and some modern electronics, so that's in my in the want ads here. So I'm getting a whole lot of antique phonographs to repair, but always interested in that stuff. And to CHRS, I want to give kudos to Rachel Lee and Steve Kushman and all the people that have done so much for CHRS and are still doing it. And I like the idea of where CHRS is going. We are getting educating younger people and having all kinds of events, and it's just fantastic. So I really have kudos for all of them. So anyway, I did bring a television show today for us to watch that features a pilot TV. So that's about it. So I'll turn it over to John Staples.
No, Joe, you go first.
My name is Joe Salcraig, and I've been with the club since about 84, and I'm pretty much into everything that's electronic, although I do like to collect and restore vintage TV, anything with CRT in it, also some cameras. The very first thing in my life that I ever was shocked by was a 1949 Zenith porthole set, so that got me off to a start. And also I'm into vintage radios. I probably have 50 sets, television sets, and just a few cameras. I came down here in about 83 from Oregon. And another thing I should mention, I really like Tektronix equipment. And I probably have about 75 tech scopes. Most of them are restored and are operating. And so like I said, I came down here in about 83 and found this club, and I've loved it ever since. I'm trying to think of what else I was going to say. I worked at Amdahl. It was a mainframe company from about that time until about 98. And then where do you go from there? Well, you go to the sewer plant. I've been working at the large sewer plant in San Jose as an instrument tech. I'm still working there, and I'm probably going to retire either in August or March. Anyway, that's pretty much wraps it up for me in a nutshell. Thanks.
Oh, okay.
Thank you, Joe.
Sorry about that.
That's okay. Hi, I'm John Staples. I'm a semi-retired scientist at LBL, Lawrence Berkeley Lab. I've been there since 1971, designing particle accelerators and dispensing them around the world. My interest in television goes back to when I was a kid. My 630 television, which I got when I was about 12, I still have it. And I have the RCA landmark for the 3 from 1946, the small, the 630, and the projection, and a CT100, everything working. In fact, all my TVs are working. My interest, as you can see, is cameras. I've been looking at and rejuvenating cameras for some time. I have a working TK-76 color camera at home. I have of course, this, another Orthicon camera, several iconoscope cameras, including a homebrew iconoscope camera that I presented here a few years ago. And my interest continues. Okay, I'm going to pass it on over here.
Hi, I'm Rob Johnson, and I've been doing basically computer, digital video stuff for most of my career. I've worked on Premiere, on the Adobe Premiere team for a while. Did a lot of digital video at Apple. I'm currently at NVIDIA. My interest in TV obviously stems from that, but I also ended up with, a lot of you guys know Jerry Grelke, so I ended up with his collection. So I'm kind of the keeper of the Grelke collection, and so that's my interest.
Where's Jerry these days? Is he still alive?
What's that?
Jerry's up in Oregon these days.
Yeah, he is, yeah. Yeah, he's doing a lot of traveling and stuff, I think, too, yeah.
Hi, my name's Tom Johnson. I'm actually currently working at LBL, working on high-energy physics for particle accelerators. I'm actually specifically working on the Large Hadron Collider over at CERN in Switzerland. I don't have any fascinating experience with television and whatnot. I'm here with my brother. It's my brother, so I'm here at his invitation. I find this interesting stuff and really look forward to learning about all this with you guys.
I'm Kurt Swanson, and I'm an electrical engineer. I designed electronics for missiles and satellites primarily. My professional television career consisted of maintaining the transmitter for one of the local TV stations when I was in college. Other than that, I've had an interest in TV, though, since I was about 13, and somebody gave me a 10-inch Spartan console that had the TV CRT pointing up and a mirror in the lid. And that started it off. I've been into TVs ever since then, so it's fascinating stuff.
My name is Gilles Vrignot. I started in TV in Tasmania as an apprentice TV serviceman and was responsible for a 4-rack TV transmitter in the shop, a monoscope, because we only had 4 hours of TV per day, 2 black and white channels. And from there on, I moved to bigger installations, building small to medium-sized TV studios for cable TV companies. And I was involved in the pioneering efforts to introduce video FM transmission in cable TV. And I built a TV head, and that's downstairs, and I work on that display with John Staples. And I'm glad to be here with lots of knowledgeable people.
Hi, Simon Favre. I'm a retired electrical engineer, also 2 degrees from Berkeley, 45 years in the semiconductor industry locally. And yeah, I had a deprived childhood. We didn't get a television until I was 10. The first thing I did after we got it was open up the back of the television set, cut one of the speaker wires, ran some lamp cord out to a switch I mounted in a Band-Aid box so we could mute all those horrible commercials. So I could claim to have invented the mute button. I later went with foot switches, so it was always, where's the switch? Step on it, step on it. And I got into electronics fairly early, and fiddled around with an awful lot of stuff, car radios. Didn't really get into the vacuum tube stuff until a few years ago. Now I have a home-based business. I have more business now than when I had an office. And I've got an Admiral 7-inch roundy at home that I replaced all the caps in and got it working. All it needs is channel 3 nowadays, so I didn't bother with any of the other channels. And at some point, I should finish, refinishing the cabinet on it, and then maybe donate it, or if someone. It's wood. Yeah, it's a wood one. Yeah, the Bakelite ones are kind of rare because they get destroyed so easily. Yeah. So yeah. Anyway, I'll pass this on.
My name is Ron Hoffman. I have no background in television. I joined the CHRS because I want to learn about radio and television communications. My career has been mainly involved with computers. I was introduced to computers in 1960 at Berkeley, and every aspect of my career since then has been related to things like communication protocols. And I'm interested in finding out today what kind of protocols were used in early television. I know now that we're in the digital age, the protocols that they use are very familiar to me, but the analog protocols are not. So I'm here to learn.
He's got a couple of sets, so I'm going to put his slide up while he's doing that. Theoretically, that'll show up.
Sorry about that. I can't see that. Oh, no worries.
You put it on the desktop earlier.
It's on my screen, it's just not on that one.
Move over. The other screen is probably off to the side of the screen that's on your desktop.
Yeah. Okay, I got to get out of
It
the.
may be off to the left or the right. Oh,
I'm going to try this. Yeah, see.
it's a nice, sharp, high resolution.
Okay, so why don't you go ahead and start introducing yourself, and hopefully we'll get to your sets here in a moment.
I'm Richard Dean. I'm from Southern California. I have a large TV collection, probably about 103 or 105 sets. Mostly 1940s. I have like two 1930 sets and a couple mechanical sets and a bunch of mechanical parts. Anything that's mechanical I was buying for a long time. I got a piece of a mechanical camera. Job-wise, I'm retired and was a system architect and computer security architect for a lot of government sites. I was closest to TV. I was a foreign broadcast information systems for a year. They wanted to look at redesigning their system for the future. And I just got a newsletter from your group here where you had a foot-operated system. Well, they had a whole big room full of foot-operated people that would fast-forward to the videotapes and rewind and stop the videotapes, and they transcribe what they see on the TVs. But I brought two sets back here. One of them actually has two names, known as the VP100 view tone, but on the ad from 1947, it calls it Futura. I never heard that name before, but it's on the ad. The other one back there is
You can point them out if you want. Let's go back and address them. Exactly right.
Okay, this is the VP100 Futura. It sold for $225 back in 1947. The date of this was November 47 on the ad. This ad here, I found it $100. It's a 1945 ad from that same company. What got me into the view tone, I found this cabinet on the right here years ago when I was looking for a chassis for it. Never found a chassis, but I found this one with a chassis in it. And they use the same chassis. The one on the other side here is from a major collector that had TVs in a castle in Scotland. And he's passed away about 5 years ago.
It's a restart. Okay.
This view tone here, the square box one, similar to the one for $100, but has a grill and the knobs have moved from the center to down below, is now owned by a guy in Florida, collector, belonged to the Buck Collection, BUK. The guy was an antique dealer in New York City, and he had, televisions from mechanical to electronic to color. He had magic lanterns, anything electronic, all kind of physics, centrifugal force things, static electricity. He had like thousands of items in the auction. I end up getting a Dumont, can't remember the brand, it's a big tall set console, no record player, no radio, and there's only, I think, 3 of those in existence from that auction. I had the Florida collector deliver it to a warehouse in Virginia, and I drove to Virginia to get it. I actually moved from Virginia to here after I retired.
Which collector in Florida?
Huh?
Which collector in Florida?
Don Sellers. Don Sellers. He's the one, if you ever look on eBay, has the pool table. The other thing here is NRI. The NRI school. Here's a student back in this picture from 1949, the magazine article from 1949. He has a 3-inch, just the top piece of this. This is a 3 chassis set. He has the single chassis. The other 2 chassis may be off to the side here, because when you build a kit, see, this one has 3 chassis that's sort of laid side by side. So I gave Tom a PDF of links to like 25 magazines for building a 2-inch kit, a 3-inch kit, a 5-inch kit, a 7-inch kit. Most of them are from the UK. I think they were more interested in the kits, especially back in the 30s and 40s than the US was. NRI basically had a lot of people on the GI Bill after the World War II going through their training. I heard that you took a kid home when you completed your course. So it's surprising. I only know of 3 of these to exist, and only 2 of them have all 3 chassis. The other one only have the top chassis. So that's about it.
Okay, my apology that his slides didn't show, but PowerPoints are working. So but thank you for joining.
Hello, I'm Ron Code. I'm from Crystal Bay, Nevada. And this is, I guess, about the 4th time I've been to this event. It's not easy to get here, so who knows? This 4th, last, I don't know. Anyway, I brought down a 7-inch set that's partially restored. It's on the back table there. Teletone, is that it? And all the high voltage part was done, so I did all the bleeder resistors, capacitors, but I'm not going to finish it, and I have a couple other sets like it anyway. And I also brought down a complete set of volumes 1 through 4 of the riders, and volume 1 is sitting back there. I'd hate to see them just go to waste, so Tom can decide if there's any fighting over any of that stuff, fine. I have no further interest in it, but I'm going to give a little talk today about Muntz television, so we'll see how that goes. If any of you are coming up to Lake Tahoe, I'm going to be reducing some of my collection, so I'd like visitors, so we'll get in touch, and with my name, Ron Code. In fact, I'm the last of the Codes that I know of, so my grandfather had 1 son, my father had 1 son, you know how it works. Thank you for listening.
My name's Carl Rankin. I've been a member of CHRS for about a year and a half now, so I'm relatively new, but I mainly was in computer electronics, and I'm an electrical engineer. But I'm also interested in the older technology. I joined CHRS mainly to learn about vacuum tube technology and the radios, because I guess my main hobby is old hi-fi equipment and stereo equipment. So that's the main reason why I joined, to learn and to hopefully save a few good pieces.
Yeah, hi, my name is John Barrio. Let's see, I joined, I don't know, 5-6 years ago, something like that. But then we moved to New Orleans a few years ago. So we're here for the summer to escape the heat. Electrical engineer, always dabbled in electronics, these kinds of things. Let's see, unfortunately, right from the get-go, I always did software. It wasn't until much later, hanging out with a group in Stockton doing World War II living history, aviation, that I actually got to get back to hardware. My exposure to TV was for one summer in, I think, early college. I came back home to New Orleans and interned at one of the big TV stations there. And so, what do you do with an intern? Well, put them behind a camera. So, I don't think I was a very good cameraman, but anyway, it was fun. Got to see a lot of what was going on behind the scenes, so that was good.
My name is Walter Spector. Just here by accident. I haven't been to the radio museum since it was up into the Berkeley radio station. And my friend Kit, who's wandering around here somewhere, was up here a couple weeks ago, and he said we should come up and check it out. So here we are. My only claim to fame with television is when I was a kid, I was on not one, but both of the children's cartoon shows where I grew up. Grandpa Happy on WHBF TV in Rock Island, Illinois, and Captain Ernie's Cartoon Showboat on WOC TV in Davenport, Iowa. I think the first TV I can remember is my parents had a Hoffman TV. It was a big thing with 3 speakers, and we actually watched the Apollo moon landing on that TV. Got my first ham license in 1974. W6WS is my current call sign, and happy to be here.
Hi, I'm Ann Dean. I'm Richard's wife. And my association with TVs is traveling all around the country picking these things up and trying to find a place to store them. We've got them in our house. We've got a storage unit, and we had to buy a house to put them in. So we have a big collection of stuff.
Hi, I'm Walt Hayden, a member of CHRS for about 20 years. Retired electrical engineer, did mainly power distribution and some industrial process control and instrumentation type things. Really don't have any significant experience with TV, but came to try to learn a few things today. So.
Okay, I'm Bob Brzeski, and I'm one of the few people here probably without any professional electronic experience. My parents were from Chicago. My parents worked in factories where they made electronic stuff. So my mom worked for Zenith, my dad worked for Teletype, and in all honesty, I spent more time in front of the TV set than I did with my parents probably. But I made a living in biopharmaceutical stuff, and I'm here because I'm interested in history. So I'm the archivist and the librarian here at CHRS. I occasionally write an article and that kind of stuff, and it's kind of fun to be here. I'm looking forward to today.
Wow. Hi, I'm Tirza Hake. Hake family is kind of local. Vern lives just a block or 2 away, and we're just local enthusiasts.
Hi, Mitch Hake. Got my start in television in about 3rd grade, having to fix the family TV. Going to the local grocery store, testing the tubes to get it running again. Been an electronic enthusiast my entire life, and here today.
Good morning. My name is Michelle. I am here with my brother and sister-in-law, Mitch and Tirza, and my brother, Vern. The only thing I could think of being related to TV is we were all on the Captain Kangaroo show. I don't know if you remember that, but I do. So it was a lot of fun. I'm happy to be here. I love history.
I'm Richard Watts. I've been a CHRS member now, I guess, for almost 20 years. I was in the 70s, I was a bench tech in a TV repair shop, and before I wandered off into computers. Then after I retired, that's when I joined CHRS and have been restoring radios, televisions, had an interest in mechanical TV and built a mirror screw. So, and just keeps me off the street.
Yes, my name is Vern Hake, life member. I live 2 blocks down, as was just mentioned. And I'm a retired merchant mariner with about 20 years of sea time. And I've worked about every job there is on the ship. In the last 2 years, I was a radio operator, which was the pinnacle of my career. And so I love radios, and that's why I'm down here now. Thanks.
Hi, my name is Alan Young. I'm an electrical engineer patent attorney for at least a few more years. I joined CHRS a couple of years ago. I restore antique radios, and I restored a TV-37U a couple of years ago with a working 3KP4 tube, and that was quite a thrill. So here I am.
Hello, I'm Kevin Hempson. I guess I got into radio about 10 years old, and by 13 I'd moved on to television. And then the BBC brought what we call an MCR, mobile control room, to the local church, and that was it. My plan was to work for the BBC, which I did subsequently do. I worked for the BBC for 10 years, and then an American company caught my eye, and I interviewed, and in 1976 I started working for Ampex. Worked a couple of years in Italy, building TV stations and placating customers. One of them was difficult. It was a guy called Berlusconi. He was very pushy. I didn't know who he was at the time. Then I returned to England and covered Europe, Africa, and Middle East, demonstrating mostly TV cameras. And then I moved to Redwood City in 1980 and worked for Ampex. I total of 17 years with Ampex, designing various pieces of gear. About that time, Ampex was starting to go downhill, and I ended up going to... Actually, first it was a video conferencing company that also did direct TV, so I got involved in those kind of products for a while. And then I ended up in the semiconductor business, and I designed chips, both analog and digital, but mostly analog chips for television. So if you've seen sync separators and video multiplexers and equalizers and things like that, I spent my time doing that. Retired, I don't know, 13 years ago, 14 years ago, and moved out into the gold country. So sadly, I can't visit this place that easily anymore. I'd love to. It's a pretty impressive place.
And I'm Tom Albrecht. I don't have any professional experience or connection to the television industry. Been interested in antique electronics from a very young age, and probably most recently, I think in the 1990s, I picked up a 7-inch TV at a CHRS meet, restored it, thought it was quite fun, and have maintained a lot of interest in the old TV sets since then. I work in a small company building scientific equipment, and also spent many years at IBM and other companies working on magnetic data storage. Okay, with that, I think we've covered everybody. Anybody that we missed? Okay, good. All right, so hopefully you heard enough little tidbits about people. that you can see what a treasure this group is, whether you're somebody who just walked in for the first time and trying to learn a little bit about antique television, or one of the people who really made history in antique television. We're great to have this group, and I hope you'll take advantage of today to talk to people and learn what you can while we're all still here and still together. Okay, with that, let's go ahead and take a look at our agenda, and we'll turn this over to John in just a moment. John will be the first speaker talking about this TK-31 camera, followed by Kevin, who will give us an update on TV engineering test gear. Then at lunch, we'll head downstairs and get sandwiches and so forth. Very important, we all need to donate $5 to a basket down there to cover the cost of the lunches, so please don't forget to do that. And while I'm thinking of things that I forgot to do, I didn't have people sign in this morning. So when you head down for lunch, stop by this table and sign in. That just helps us keep in contact with you for future events. Then after lunch, Ron is going to give us the confessions of a month's salesman. That'll be fun. And then Nat Pendleton, he's not here yet, but he'll be showing up soon. He's going to talk about the introduction of UHF TV. And then John will come back to tell us more about this camera project, the camera control unit, which is a project in itself. So we'll hear about that later today. And finally, we'll wind things up with a nice vintage TV show that features a vintage TV as part of the storyline of the show. So that's something a little different. We did something like that last year as well. So that'll be what we finish the day off with. Okay, with that, I think you can use the lav mic.
We're on the lav.
Good. You're all set.
We're going to pull the TV display over to the other computer, and hopefully we have less trouble with this one. Okay, thanks guys. I'm John Staples again. I'm a TV nut. Cameras, I've all the way from mechanical up through modern. This camera I acquired fairly recently, not my only camera, but it's my biggest one and my heaviest one. And let me tell you a little bit about it. Let's take us back to 1952, actually even a little earlier than 1952. Do we recognize some of these people?
Oh, yeah, I do.
Jackie Gleason, right there. The Shore of Shows, Ed Sullivan, John Cameron Swayze. I was born and grew up in Chicago, I think like some of the people here. Kukla Frananale on WBKB, the first station in Chicago. That show ran from 1947 through 1957. It went national, and the national was originated from Chicago. And I was watching that program back then. Back in '53, this camera, by the way, is vintage 1952. Back in '53, 80% of television was live. This was before videotape, which was introduced in 1956. RCA premiered back in their channel 1939 World's Fair. That's a 441 line system. The NTSC, under the direction of Dr. Baker, finalized the standard. There was, in about 1940, it turned out that Donald Fink, who was an electrical engineer on the NTSC panel, rumor has it that the night before at his kitchen table, he kind of worked it out and recommended it was going to be 525. Other people wanted less. Philco wanted more. 525 turned out to be the scanning rate that we've used ever since then. The television started before the war, but during the war it was all shut down basically. There was still some broadcasting, but the World War Procurement Board lifted that ban after World War II ended. In 1946, RCA, by the way, the earlier camera was an iconoscope camera, the 1939 camera. In 1946, the RCA TK-10 was introduced. The terminology is the TK-10 is a studio camera. The TK-30 was the field camera. Both cameras were identical and completely interchangeable. I mean, they were identical, so they had to be interchangeable. The TK-10 used a studio camera control unit. The TK-30 used a field camera control unit, and you can see right here. This is the, these are the two camera control units for the TK-30. This is the switcher. This is the monitor, the waveform monitor and the line monitor. Down here, power supplies, and these two modules here were the sync generator and the pulse amplifier that went to the cameras. 1946. In San Francisco, the first station on the air came on in 1947. Secondly, Cron came on a year later. Here's actually the Cron control room being assembled in 1948. I found a name of Al Eisberg, the chief engineer, who on the left. Did anybody recognize that name? I don't. This is before my time. Now, RCA had a catalog. RCA was really promoting television at this point. It had a slow start in the public. Sarnoff was really pushing this. So RCA published catalogs of television station setups. And they had this beautiful, it was done with little models. They would put together various scenarios from just doing film and network broadcasting to having a single camera, having multiple camera installations. They would have a complete floor layout. They would come in and set it all up for you. And you can see here, this is a two-camera setup right up here. You can see one camera on talent and another one there on probably a poster board. The control room would be right here. This is the film chain right here. You can see an iconoscope film camera. I think that would be a TK-20. Here is the transmitter. So the transmitter would be at the same building as the studio. And way back up here are the control racks providing the sync, the power for all the equipment. And this is what would be in those control racks. Here is the sync generator. These sync generators provide the synchronism pulses for the entire facility. There was two of them. Everything, of course, was vacuum tube. And if you lost a sync generator, you've lost everything. Most of the rest of this is power supplies, video amplifiers, distribution amplifiers. But that's how these things looked when they got started. Let's talk a little bit about the pickup tubes that lead us up to the orthicon that's in this camera. Of course, the very early cameras were mechanical. There would be, for example, one way of doing it is taking an arc light, putting it through a disc with spiral holes, and illuminating the talent with this sweeping light with a number of photocells around it. Here you see 4 photocells. It turns out that the more photocells that you can put in, the better the signal-to-noise ratio. The photocells all see the same scene, so the voltages add linearly, but the noise is all random, and they add up in quadrature. So the signal-to-noise ratio of these mechanical cameras improved as to the square root of the number of photocells that you could put on the talent. Now, this only worked in a darkened studio. If you want to do an outside, you'd actually have to reverse things. So now the photocell, there will only be one at this point, would go back through the scanning disk to the scene, and it would pick the scene up. You'd have to have a lot of light on the scene or to get a picture at all. But Farnsworth came along with the image dissector. And this was the first of all electronic system. It predated the system the RCA and Westinghouse and stuff came up with. And in the image dissector, you focus the lens on a semi-transparent photocathode right there at the front of the tube. This is one of the configurations. And the electrons are emitted from this photosensitive layer, and they are focused back to a little pinhole in the back, and behind that pinhole is a electrode that picks up the signal. And this is really an electronic version of a mechanical television. The whole image is coherent. The image from the photocathode, you focus it with a longitudinal focusing lens, takes that electronic image from the photocathode and scans it as analogous to a mechanical scanner right across that aperture, and the signal will come out. Now, other versions of this image detector kind of reverse. They put the photocathode right behind at the far end, and then they have the electron pickup at the front of the tube, and usually including an electron multiplier, which is a very good wideband, low noise amplifier. The Farnsworth tube, the image detector gave good resolution, but it was still very poor, very low sensitivity. So how did they increase the sensitivity of these tubes? And they used what's called storage. These tubes, just anything that was not going through the little slit, any information was just thrown away. But if you could take the entire image and store that image and then read it out after every field is scanned, you could build up that stored image, and that's what's happening here on the iconoscope. The signal plate on the iconoscope is a bunch of very small, little, insulated from each other, little globules. What they would do is they would plate silver on a mica back substrate, for example, heat it, and the silver would coalesce to a number of little individual disconnected little globules, and you can sensitize it with cesium, which makes it photosensitive. And so focus the image onto that plate, scan through it, and from the time it takes to scan to the next time it comes out, you have built up that electrical image on those little individual you might say photocells on that image plate. It turns out that it was quite a bit more sensitive, but there was a lot of things that didn't work very well. For example, the electrons that would come off of this, particularly when the scanning beam hits this backplate, causes a lot of secondary electrons also to be emitted. And so it turns out that this whole region here was kind of a fog of random electrons. And so the actual efficiency of the iconoscope was probably less than 10% of its theoretical possibility, but still an improvement in sensitivity over the Farnsworth image detector. But that takes us now to the image orthicon, which turns out to be quite a sensitive tube. The problem with the iconoscope is that this beam that was hitting the signal plate, which is the beam is accelerated to about a kilovolt. That kilovolt, when that beam hits the target, that signal plate, it does eliminate a lot of electrons. If we could scan that plate with a beam that had an energy that was less than enough to knock electrons out, then we could deal with that problem of secondary electrons not being emitted anymore. And that's exactly what the orthicon does. The orthicon will generate a scanning beam at a few hundred volts, but as the scanning beam goes on toward the target, its energy is retarded. By the time it gets to the target, it has an energy of about 2 volts, and that's all, about 2 volts. And the image on the target, whenever there's light, the target will start turning positive because it's losing electrons. Electrons are negative, so it starts going positive. So there's an image on the target where the bright parts of the scene are more positive. The dark parts of the scene remain negative. And when this beam comes to the target, when it finds a place that's positive, that's where its light is, the beam will go to the target and recharge the target. But on those other places where the target is not illuminated, the beam actually turns around. It sees, electrons, the light charges repel each other. The beam has an energy of about 2 volts. The beam turns around goes back, doesn't go back through the little hole in the electron gun, but it finds its way to a 5-stage photomultiplier, and that's the actual video that comes out of this, and it can be quite strong. Now, you also find that this is called an image orthicon, not just an orthicon. The first tubes were orthicons, and they eliminated this so-called image section right here. The image section is the same sort of thing, you know, these World War II Army sniper scopes, the light amplifiers and things like that. They would have a photocathode that would see the scene. And then the electrons will be accelerated to a phosphor target in these sniper scope things, light amplifier. In this case, the same idea. The photocathode, the beam is generated here just the same way it's generated up here in the image detector, and goes to the target. And that additional amplifier right there, now it's called the image section, that distinguishes an orthicon from an image orthicon, and it gives it sensitivity increase about another factor of 100. So the orthicons really, the kind of illumination we have in this room right now would be just fine for an orthicon camera, and would give a good picture. Okay, let's go on, talk about the camera. In May of 1952, RCA brought out the second version of their studio and field camera, the TK-11 and the TK-31. The 11 is the studio camera, the 31 is the field camera. They're electrically interchangeable. The only difference between them is that the TK-11 has a studio camera control unit. The TK-31 is the field unit. And that's what this camera is right here. This is a field camera, TK-31B. I haven't been able to find out why the B is different from an A, or whether there is even an A. But this is the camera that we have right here. This camera actually came from a state. The fellow, his name was John Bolin. His son, Scott Bolin, is the person who actually contacted me, and contacted also Kevin, who was also lucky to find three cameras here at the Bolin estate. And his wife, Jackie, Jackie is the wife of the deceased, and Scott and some other people there gave this camera to both me and to Kevin. It's in very good shape. Our best guess is, or Scott Bolin's best guess is, that he probably came from a movie production lot that provide just props for movies. So this would have probably not been on the air, at least at the time that Bolin acquiesced it, and probably the reason it's in such nice shape, that it was used as a prop for Hollywood productions. Anyway, it was very generous of him to provide us with this camera. I picked it up over at Scott's place, loaded it into the Tesla, brought it back here, and this is the camera. First day it came on in, and the water on the patio, I was hosing down some dirt that was on the wheels, and there it is. A couple more pictures. Again, this is from the first day this camera came in, and just sort of circulated and sort of show it to you. I mean, in the back of the camera are the setup controls. In fact, even on the side of the camera, there are 19 setup controls for this camera. These controls are not used when the camera is on the air. This is all done ahead of time. The cameraman has got enough to do, just focusing, moving, acquiring, and there at the other end of the cable of this camera in the control room is somebody who is actually controlling the fine points of this camera, adjusting the camera to accommodate for the scene brightness and some of the focus. The documentation for this camera was supplied to me by Kevin. Kevin had a copy of the original RCA manual for this camera, which was really helpful, really something that was really needed to be able to restore this camera. There's also a book by this fellow by the name of Howard Chin. He was part of a team that was doing training for people running these cameras. He ran a training school. I think it was associated, but not quite, with RCA, which kind of got me started. Here's Kevin's documentation, and all the RCA cameras seem to come in red binders. So I found a red binder. And these are my own notes that I make during the restoration process, so to kind of keep it straight in my own head. And then for the printing out all these schematics as large as I could see. Here's the inside of the camera. I've already seen the left side. The left side here is the basically the deflection. This is the deflection and high voltage side of this camera. The deflection amplifier is vertical, horizontal. And on the other side of the camera, right here, this is the video amplifier, right there. The video amplifier is rubber mounted, and the rubber after 70 years is still good. Each tube in this, there are 4 stages of gain there. Each has a gain of about 2 or 2.5, because they're very wide band amplifiers. The thing is flat to about 10 megahertz. But to get a very wide band amplifier, and these are 6AH6s, they're very hot tubes, you don't wind up with much gain because they're very heavily compensated to get this gain, and also keep the group delay to a minimum, which keeps the picture from being, keeps the picture quality good. Here are the operational controls in the camera. You can see right here we have in the back of the camera, and these are again all setup controls, centering, scan widths and heights, linearity. This camera also will do film, and I don't quite understand this. To do film, you actually are inverting the vertical scan. So there's a separate centering control to invert the vertical scan in this camera. These controls here, G5, G6, what they're associated with is some of the grids inside the image orthicon, and if there was geometry, you adjust those so that straight lines don't have little bends and things like that. That's what these are. Well, I won't go through the detail. Here's some of the details. Inside this camera, on this side right here, on the right side of the camera, down near the bottom, you see a switch that's called S, M, and L. What this is, this adjusts the 120 volt, or compensates for the drop in the 120 volt AC that's coming into the camera filament transformer. If it's for S, that means we have a short cable to the CCU. If it's L, you have a long cable, maybe 5,000 feet to the CCU. And what it's doing is it's adjusting the tap on the primary of the filament transformer in both the camera and the viewfinder. And in the L position, they assume it's about 80 volts. That finally, 80 volts of 120 volts that finally makes it to the filament transformer in the camera. Now in the CCU, there's a similar switch, and what that does is it adjusts for the loss of high frequency in the cable itself. And so if you're close, you dial in one setting. If it's long, it actually peaks up the high frequency, the compensating for the high frequency loss in the coaxial cable from the camera. So this camera has 7,500 running hours. I tried to find out if there was a registration for these cameras. I talked to Chuck Ferris, who has almost 20 of these cameras in various conditions. He didn't know either. if there was a registration. You know, there are registrations for televisions. There's a registration, for example, for CT100 televisions. You know, Ed Rytan was doing it, now somebody else is taking it. Since his death, somebody else is taking that over. No such thing exists for this camera. It's called an image orth, not an image orthicon camera. Image orth. Part of the 11 and the 31. Again, the 11 and the 31 are one and the same camera. Here's what is the block diagram of what's in this camera. Right across the top is the video amplifier. That's the one that you see right here. This is the video amplifier, right there. And what that does is that puts out eventually about a fraction of a volt of just raw video, raw unprocessed video that then goes off to the camera control unit. And the rest of it is all deflection circuits, a high voltage generator within the camera. The orthicon needs about 1500 volts to operate, and that's done here on this side. This is all deflection chassis and high voltage generator in the camera. When I got it, of course, I wanted to start off simple. So the first thing to do is actually try to make the viewfinder work. It's a television set. In fact, it's actually a fairly simple television set. So I started working on this one. It needed a lot of recapping. It uses a 7-inch tube with 10 kilovolts on the anode. 3 external controls, contrast, focus, and brightness, just like on an ordinary television set. But there were some other things inside. The viewfinder sits right on top of the camera and connects to the camera through this connector right here. That connector on the bottom of the viewfinder and on top of the camera. Now that viewfinder, rather that connection, made it kind of hard to get wires to it because I'm laying the thing on the desk, and so I was just patching various voltages into the camera, getting it to work. The viewfinder needed some recapping. The major components are all just fine. And so what you see here is I'm taking a really nice sync generator, which I eventually used for the entire system, a power supply, running the camera. And I'm feeding from the sync generator the color bar pattern.
Isn't that CRT a projection type?
You're thinking of a 5TP or 7TP4. It's aluminized, but it's not the projection tube. You're thinking of a 7 or 5 TP4. It's similar, but it is not the projection tube.
Okay.
Yeah. And by the way, if other people have questions, just pipe up. The question was that tube in the viewfinder a projection kinescope? And the answer is no. It was not the projection kinescope that you might be thinking of.
They actually did make some projection sets with 7 TP4s also.
Yeah.
But it was primarily used in that camera.
Okay, the comment is that they actually did make some projection kinescopes that they could have used in that camera. Probably very little different. The projection kinescopes, run at 25 to 30 kilovolts, and this one runs at 10 kilovolts. But it is aluminized, and it's a very high def CRT. And in fact, here is the color bar pattern with the standard bars, and you can see here the chroma grain. Then the chroma grain, the bandwidth of the video amplifier here is just about flat to at least 8 megahertz, and the chroma grain just completely modulates the image on the face of the CRT. It's a really high definition CRT showing complete modulation of that chroma grain. So it's quite a nice viewfinder. The schematic again. Video amplifier, conventional deflection. It's not a TV set because there's no sync separator or anything like that. The sync signals are separate. There's still what's called the horizontal and the vertical drive signals. There is nothing available to the viewfinder, which is a standard television sync signal. So the horizontal and the vertical drive come in. They drive conventional components. But there's something rather interesting here at the exit of this whole business. And what it is, these are a set of multivibrators. In other words, they're square wave generators with variable widths that are used to create a blanking signal for the viewfinder. In other words, what it is the viewfinder. You can, with the controls in the viewfinder, you can actually control the window both horizontally and vertically by adjusting the period of these multivibrators. So you are adjusting the window. You can eliminate parts that are outside of the image. The TK-10 camera did not have that feature, by the way. Okay, here the lens turret. This camera has 4 lenses. The focus for this camera is right here. And this moves the orthicon assembly back and forth. This guy right here. That moves here's the gear. There's a worm gear mechanism. This worm gear mechanism is attached right here to the orthicon assembly. The orthicon assembly drops down onto the top of this camera. Here's what it looks like disconnected from the camera. This is the heaviest part of the camera. This is a steel magnetic shield. This whole assembly here probably weighs about 20 pounds or so. It's the heaviest single element in the camera. The lenses, this camera came with 4 lenses, a little unusual. Usually there's 3 lenses. Usually there's 3 lenses and a blank off, where you would normally leave it when you're not using the camera to keep the light off of the orthicon. This camera came with 4 lenses, a pair of 90s and a 135. Manual iris. These lenses were not adjustable during programming. So you'd have to rehearse the event in the studio, figure out how much light was optimum for the camera for each one of those, and pre-adjust the lenses. Now, other lenses had a feature that you could actually vary their aperture, but not this one. So of the two 90s, what I've got is I've got one stopped all the way down, and I use that as the blank off, and then the other one is stopped open.
Was there like a variety of lenses that were available, or were it all the cameras that basically had the same configuration?
Yes, the question is, were there a variety of lenses available for these cameras? The answer is yes. You look at the RCA catalog and they had pages and pages of various types of lenses. Some of them were the early zoom lenses, and it turns out that the lens changing mechanism right here, the shaft for this thing was actually hollow. And a focusing rod for some of the lenses would actually extend all the way through to the front and then connect to the zoom or the aperture of at least one of the lenses. The word is that stick that went through the hollow turret system was very critical that it would be straight. If it was at all bent, it would jam up. So the camera operators would take that home with them and then bring it back the next day. They wanted to protect it because they had so much trouble with that getting bent and getting stuck. The cable to the camera is a 24-pin cable, and it did not come with the camera. And so I had to assemble one, had to actually find connectors, and a little bit of scouting around. I did find one new in box on eBay. It turned out that if you look for camera connectors and say, well, I'm looking for camera connectors on eBay, you don't find anything. But if you know the actual part number of the Canon connector, search that way, that one showed up. And these things are unobtainable. That cost $21, new in box. Unbelievable. Lucky. Now, of these 24 cables, 24 connectors in here, 3 are coaxial connectors. One of them is the video coming from the camera back to the camera control unit. The other 2 are the horizontal and vertical drive coming from the control unit into the camera to synchronize the camera. And all of these other are providing various power. Power 120 volts for the filament transformers and so on. The camera, the orthicon itself requires temperature control. The front of the orthicon tube, this very, very thin glass plate, which is the target, likes to be at about 50 degrees centigrade. 50 degrees centigrade. And so there's a built-in heater and blower mechanism that controls that temperature. Here's the blower right here. The blower, this pipe or this hose from the blower connects up into the orthicon assembly. And it has to be flexible because the orthicon assembly is moving back and forth. When you focus it, had petrified, but found what was called bilge hose, what actually worked. So that's in there. The control for that blower is right here. You could turn everything off. You could turn it on to automatic, which would, there's a thermostat, the blower, and there's a heater. They would go back and forth with each other. Or you could turn it on blower only or heater only. So you had four options for controlling the temperature of the orthicon target. You can see here, looking down you pull the orthicon assembly off, and you look down from above in what I call the canyon. There's a steep canyon. You're looking down into the canyon from up above, and you see the blower up there. Here's the blower. The tube that goes up into the camera, and a bunch of transformers and electrolytics are kind of all poking into this canyon, which is right in the middle of the camera. Underneath the camera, you can see where the camera mounts to the pedestal. Screws in here, and these jacks here are for the interphone system. Now, the interphone system. 5 wires in that camera cable were devoted to the interphone system. The interphone system carried 4 audio lines and then a common program A and B, or engineering and production. If you're setting the camera up, you're talking to your camera control unit operator in the control room. You tune into the engineering channel, and between the 2 of you set the camera up. You can see here, this is what the camera operator was actually using, which has a nice long wire on it. And there's a second connection, there's a second jack on the camera that will be used, for example, your floor manager, your floor director. And he'd come on over, and probably the camera that's nearest to him, he'd plug his interphone into the other jack that's available on the camera, and he'd be working with the director. Program A and Program B, I guess you could also see what's going on. Now, the interphone system was actually present in the 1939 camera. It was actually included in that. RCA knew that for production, already for production, you actually had to have that kind of communications to the camera operator even in 1939.
You mentioned a little comment. You mentioned the high resolution of the monitor on this. early color televisions had the opposite problem, that early color televisions would get confused by black and white programming because it had such high resolution. You would see color fringes where the TV thought it was decoding the chroma, and it was just a black and white program.
Black and white televisions were not able to show you color on the screen.
Well, yeah, but this was the opposite problem. This was a color television with a black and white program.
If the color television didn't have a functioning color killer. But you're right. I mean, and of course, this persists to this day. I mean, even now in high-def TV, if somebody's wearing a shirt that has all sorts of detail, you can start seeing moire and interference patterns. Gilles, you have a question?
John, yeah, I have a question about the temperature control for the pickup tube.
Yes.
What visual effect do you have as the temperature is coming up, or if it's not the right temperature?
Okay, good. That's a very good question. I have another orthicon camera, and it turned out that that camera didn't operate until I got the temperature of the target up to an elevated amount. I think the orthicon for that camera was probably not very good. The orthicon for this camera seemed to be in much better shape, and I can get good pictures of it immediately. And I've never left the camera running long enough to allow it to achieve a stable 50-degree centigrade temperature. So I can't answer your question directly, but I think with better tubes, you probably have more latitude. With my other orthicon camera, I really needed to warm up in order to start getting anywhere near a decent picture.
So you did not observe, for example, a resolution chart while it was warming up?
I don't have enough information to really answer your question, but it's a good question. Talk a little bit about this field tripod for this camera, and it's really quite a piece. Made by Houston Fearless. Fearless is an adjective, now not an adjective. Turns out that Houston, from Texas, of course, about 100 years ago, started making equipment to support the photograph industry at that time. After a year or so, he moved to Southern California, found this fellow Fearless many years later who was sort of in the same, doing the same sort of thing. They combined, formed their company, Houston Fearless, made these top of the line tripods for these cameras. By the way, this is a monochrome cradle head, and it does have the RCA logo on it, which is really nice, so it's authentic. The monochrome cable head. If this were a color camera, that camera would be weighing 350 pounds. This camera here with the viewfinder weighs 109 pounds. And this thing, the way this moves around and just glides, it's heavy. We've got 150, nearly 200 pounds here. And, this tripod is really quite remarkable. It has all sorts of adjustments on it. Over on this side, there's adjustments for the how stiff I want the pan. Other adjustments, how stiff I want the. And down in these parts here, all sorts of adjustments to how the wheels are going to work and how to lock it up. There's an adjustment that adjusts the camera longitudinally, so you can actually balance the camera, so it has a neutral balance, and that's and those adjustments are all made through. I think. Do I have it here in my pocket? Made through a key, right? Like this key right here, which you insert in various places here, and make adjustments. In this, we have a question.
Is there any adjustment for height?
No, good question. Is there any adjustment for height? The studio cameras, yes. The studio pedestals would have a compressed air or compressed nitrogen system that would actually allow and balance out the weight of the camera. The cameraman could then easily lift the camera and cause it to go down. Also, a big ring that you could actually manually steer where the wheels are going to take you. The answer on this one, no. No height adjustment. And the wheels themselves are easy enough to, maybe I've got that, oh, that one's locked. See, now I can do that. That's one of the adjustments of this camera. Turn these wheels here, I can actually fix the camera to the floor.
Was this a studio tripod or a field tripod?
Was this a studio or a field tripod? This is a field tripod. And that's what makes this camera TK-31 instead of a TK-11, which would then have been a studio pedestal on the camera. Okay, a little bit on the restoration of this camera. I started off on doing the viewfinder, getting the viewfinder working. A lot of recapping. I pulled this 24-pin connector off the camera, making sure that everything is okay there. This is the video amp. Here's the kind of all pieces of the various parts of the camera kind of all laid out. Here is the video amplifier that came out of the camera. And that's on the right-hand side. This all right here. And here is it unplugs, by the way. It unplugs through an octal socket right here. Octal socket right there. It has one input at that end, 4 stages of 6 AH6 high transconductance pentodes, and then a cathode follower output system right here. 2 outputs. One output right here goes right up to the viewfinder. The second output underneath it right here goes out to the cable and out to the camera control unit. This is what the video amplifier looked at. 4 stages of 6 AH6s and then cathode followers and a low impedance output driver that drives the video into the amplifier. The gain of each one of these stages, these are pretty hot tubes, these 6 AH6s, typically gain in one of these stages is about 2.5 voltage gain because it's so wide band. In order to get the camera running, I needed a power supply. And so I found a chassis. The chassis looked like it was a little ham radio transmitter of some sort. I cleaned it off and put some power supply on it. You can see the connector. And the important controls that are in the camera control unit, in the control room, are these controls right here, the beam and target control, which control the details of the orthicon. And then these controls here control some of the other electrodes inside of the image orthicon. So these are the, not for the camera operator, these are not setup controls. These are the controls that are used from the control room during actual program generation. So power supply, I needed to put together a power supply to run this thing. And you can see here's the carcass of the camera on the workbench. Here's the sync generator I'm using, an oscilloscope. And I've been through this several times. I've put several cameras together. And the first time you get a picture, like first light, it's like the first time a telescope works, you get first light. And it's really exciting just to have anything that tells you that something is working. And so that's what it looked like, and I said, wow, that's just really terrific. But it gets better. And so this is the setup. These power supplies, fortunately I had in stock, they're 300 volt, 400 milliamp power supplies. Each one of those power supplies has got 6 6L6 pass tubes in parallel, and they're really heavy. Each one of these weighs nearly 50 pounds, and that's the reason they're not here today. But that's when I first started getting this thing running. You can see here in a little more detail. The Heath kit supplies the power for the solenoid of the focusing for the solenoid magnet for the orthicon. That magnet dissipates over 10 watts, so it's going to heat up. And if you provide its power from a constant voltage power supply, as it heats up, copper is going to start getting a higher resistance, and the current through is going to start falling. The regulation of the power of the current through that focusing solenoid for the orthicon is really critical. And so that current for that focusing solenoid is delivered from a constant current power supply and not a constant voltage power supply. Anyway, pictures kept getting better and better as I learned how to tune this thing up. And here you can see the video coming out of the camera. It doesn't really look like real video, doesn't it? There are no sync pulses or anything like that. But that's what's being displayed on the viewfinder of the camera. The viewfinder is showing you the raw video, unprocessed, coming out of the orthicon. So you can see the power supplies. These things are running. You add these two currents up, you're running about 0.6 of an amp at 300 volts going into the camera with through that power supply. So stay tuned for this afternoon. But I'm going to bring you back to a comparison of this camera to its father, the TK1, the TK10 versus the TK11. And so the TK, you can hear this, the TK1, this is the studio, and this is all the studio pedestal for this camera. TK11 would have also the same kind of pedestal. The field camera, the TK30 and the TK31 would have the tripods. It turns out that the 1946 camera and the 1952 camera are completely plug interchangeable. Use the same connector. In fact, a lot of the other camera equipment that RCA was having, for example, their film chain and some of the other cameras, were all using this very same 24-pin connector because RCA said, you're going to have a lot of infrastructure in your studio. We want you to be able to upgrade without many changes to your infrastructure. So for a few generations, they used this 24-pin connector. When they finally got to the point where they wanted the program material to be actually presented on the viewfinder of the camera, rather than what the camera is actually seeing at that point. Feeding video back into the camera, for example, you have two cameras that are trying to do some fancy graphics or commercial, something. You want two cameras that would focus in, sort of combine a picture. How do you get that video from the control room back into the camera? There's no coaxial cable there to allow you to do that. So what they did is they took the vertical drive cable and fed video back through that, and then the vertical drive signal, they modulated on a 15 megahertz carrier and fed that back through the horizontal drive signal. Well, you got to do what you got to do. A little bit more of a comparison. The TK10 had 16 tubes, the 11 had 20 tubes in it. The viewfinder had 12 tubes, the TK11 had 19 tubes, and most of the 19 was that windowing mobile vibrators that were in there that allow you to sort of adjust the part of the image that was actually visible, and the rest of it would be blanked out. The viewfinder went from 5 to a 7-inch at a higher voltage. The temperature control for the orthicon is a snap. Up near the front of the orthicon is a snap temperature regulator. It's a kind of a bang bang kind of circuit that would either go on or off. And apparently, that going on and off, that transient, was interfering with the camera. So what they did is they had a filament control consisting of a 6x4. Now, a 6x4 is not a gridded tube, it's a rectifier. It's a rectifier. So what did they do? What they did is the snap would actually control the filament of the 6X4, would slowly turn on, turn the blower on, slowly turn off. And across the 6X4, well, there's a selenium in the other polarity. And so that was always there, but with DC going through the selenium, but not AC through the 6X4, the fan motor would not run. But as soon as the 6X4 got hot, then you had the selenium in one sense, the 6X4 in the other, and the fan motor would start. So 6X4 used as a control tube. Interesting. There was a protection circuit for the orthicon. If the scan voltages were not there, then it would not apply the high voltage to the orthicon. Anyway, that's my talk. This afternoon, I'm going to talk about the design and construction of the control unit sitting right back there on the table. Any other questions?
Thank you, John. That's a wonderful.
Great. Thank you.
One wonderful piece of work and some very nice documentation in your presentation.
And please, the cameras, we'll have the camera here all day, and just come on around and poke around inside here. It's a really interesting, it's a really historical and interesting piece of equipment.
Yeah, we're a little short of time now, but I thought we'd allow one question. Of course, John will be back this afternoon, and you can ask lots of questions then. But anybody want to pose a question now to John? If not, save it up for lunchtime and when he returns this afternoon.
Well, good afternoon, I think. Maybe it's still morning. So I started off, I got interested in test gear. As I said, by 13, I was mending televisions and frustrated by the fact that the test card was on very rarely. So I built my first piece of test gear at about 13, and it was OC45 transistors, I think they were called. It was over here we call it a crosshatch pattern. In England in those days, it was a grill generator, spelt with an E, grill with an E. So there's kind of three areas that you measure things in television. There's actually more, but I've left out transmitters themselves because you get into a lot of other stuff. This whole thing actually should probably be a whole week of talk, but and I also left out videotape recorders. Despite working for Ampex for many years, they're kind of specialized as well. So really, we're looking at three areas. You've got the beginning of television, where you're capturing with a camera, you're capturing some kind of image and turning it into some electrical signal. Then you've got to get it from the capture device out to the display device. So in this case, we're talking about a wire or maybe a fiber. And sometimes microwaves, of course, are used for transmitting the image. So the input, optical to electrical, everything originally involved scanning, as John has already taught us. It was mechanical or some kind of mostly magnetic scanning. And sadly, magnetic scanning is not the most linear of processes in the world. So there's a lot of things in there to measure scanning linearity and sizes. And once you get to color, of course, a little bit of a rotation error matters as well, because all 3 tubes or 4 tubes in some cases, they all have to be on the same horizontal. So rotation is also another aspect. Then we get into the signal itself. Once we've generated it, and we're interested in, are the blacks accurate, are the whites accurate? The gamma, the transfer function, is it linear from black to white? Overall, from the camera image to the visual image at the end. And tubes have an error in some of the tubes. The scan is scanning across, and in some tubes it's not perfectly orthogonal to the target, so you start to get some kind of shading errors as you get to the edge. Or on things like the Vidicon, they're notorious for. The edges are slightly non-linear because the thickness of the coating is varying. So you need to figure out, is the scanning linear? Has it got some shading on it? And then finally, you've got, particularly later on in the color signals, you've now got another process, the coding of the signals, to make sure that that you get the color there accurately. So for the camera part of it, and also there's, of course, there's telecines and slide projectors where it's slightly different. But first of all, you've got to get some kind of image into the system to analyze, is the camera doing the job right, assuming the monitor's working right. So in this case, does that work? Not very well.
Use the red.
Oh, you've got a stick somewhere.
Yeah. Oh, man.
Oh, there it is. Okay. So, you know, if you're not very rich, you're building up kind of a basic TV system, you often relied on something that's arrived in the camera manual. And the Japanese kind of upped it a little bit. They made much nicer test patterns printed on, mounted on a piece of card, so that was a big improvement. But you could, companies did specialize in making test patterns, and those were nice, but they were pretty expensive. So you could get large cards with a test pattern on, or these little, this is a little holder that holds 4 patterns in there, and you can change them, you can set it up in front of the camera fairly well. But a system like this, you know, this is called porta pattern, and we're talking thousands of dollars for one of those, so it kind of really made it a lot more expensive. These, of course, you had to light them, and you had to light them nice and evenly as well, because if you didn't light it evenly, you may have shading that you're going to try and measure. But sometimes one of the problems was people walking, very often the camera control unit, where you were doing some of the setup, was 2 stories above the floor of the studio. So you'd climb all the way up there and you'd get up there and you'd start controlling, and somebody would walk by and catch the pan bar. And you had to go all the way back down and realign it. So, and other things happened as well. Somebody would get in front of the pattern. One of the TV stations I went to in Syria, I've never seen so many rats in my life. There were tens of thousands of rats. And one day I'm doing something with one of these patterns, and there's a funny shape in the picture, and sure enough it was a rat sitting there in front of the test card. So it is nice to have, this is a light box, it generates light, and you put a transparency in front, and that's a nice solution. It's fairly expensive transparency, but it's a big improvement over the cardboards ones. Even that, though, somebody can walk in front of. So there is another system where we have these things which are a little projector. And basically, it's very expensive. So basically, you've got a light unit at the back, and then the projection assembly, and then an adapter to get the correct adapter to whichever type of lens system. Most of mine that I've found over the years are C-mount adapters. The one at the back there is custom for a special ingenue setup. And it has interchangeable patterns that come on little slides. Quite small slides. And one of these setups, a kit with just enough items to do the job. This is one of the slides, by the way. These are about between $200 and $500 a piece in the day. The whole kit, the projector, the adapters, the whole system, this is a slight, these have got a nice illumination in them. It's basically a sphere to give a very even illumination. This has a simpler one
with just a lamp. But the kit, which includes one of those and a power supply, and the basic requirements for the slides, is about $12,000. So it was an expensive setup. There's a collection of some of the slides. You can see there's grayscales, test cards, frequency response tests, and the grill, the crosshatch for colour work. And this one, which we'll get to in a minute, called a bubble chart. I did take a few photographs of these in operation. I wanted to use one of my other cameras, but they weren't really available at the time. So I took this. This is probably an 80s camera, it's Thomson CSF camera. And I don't have an adapter to put it on a tripod, so I had to strap it to the tripod with some tie wraps. The reason that this ended up being the camera of choice for this was that some of these tests rely on being in synchronization. The camera and the test pattern must be synchronized to each other. And turns out my generator wouldn't lock to an external signal, and several of the other cameras wouldn't lock. And the one that did was PAL, and I didn't want to have to mess with PAL and NTSC all in the same deal. So I used this little Thomson CSF portable camera, which amazingly still works quite well. And I used that. I could point that out at what's called a bubble chart in this case. You see a somewhat larger lens over there, and I'd hoped to demonstrate a couple of effects of the lenses, but it didn't work out. Sometimes the lenses add their own image distortion. It's not just the electronics. So lenses, as you zoom from wide angle to telephoto, will often go through a set of distortions. There'll be one point in the zoom ratio where it's fairly good, but then you zoom back or in and you'll find you've got pincushion distortion at one end or barrel distortion at the other end. So that can get a challenge. So the bubble chart, which we've seen a couple of times already, I brought this one up because it's a little less familiar to people. Well, what's happening here is the camera takes an image of the bubble chart. The electronics generate the crosshatch. And I found out that my crosshatch generator needs aligning because I can't make it work for verticals and horizontals. And had it just been this tube camera, I would have blamed the camera. But I also ran it with a little CCD camera, and the CCDs are pretty good. They're always the correct aspect ratio. But what you do here is you make the crosshatch in the center of the bubble on the left, and also on the right. And going horizontally, those are about correct. But as you go across, and you see even on there, you see this one and this one off horizontally from the center. And so that shows that the horizontal scan of that particular camera is not quite linear. It's good enough, it would pass its, I don't know what the specs are on that Thomson, but if it sits within the white part of the bubble, it means it's within 1% linear. If it sits within the black part of the bubble, it means it's within 2%. Most cameras in that era were specified at about 1.5%. Another reason I chose that particular CSF camera was that it has monitor outputs on it for setting up the color features of a camera. So one of those features, and you can do this with some Tektronix monitors as well, one of the features is there's your usual test card, may not look right though, and it's inverted. It has a minus, and that's from the green channel of the color camera, so that's a minus green image. And the reason you have a minus green image is because you want the green, the red, and the blue to be all registered on top of each other, just like when you're setting up a color tube. So you take one of these crosshatch patterns, and this is the green image coming out of the camera head itself directly, not coded. on this particular camera, I wanted to use a studio camera, but I just couldn't. I haven't got the space at the moment. This one, you can't turn off the enhancement, so you see it's kind of bright white on either side of the black lines. Normally you would turn off the enhancer to do this test. So we take the minus green and we take, in this case I've forgotten what it was probably the red or blue, it was the red or blue, but it's probably the red I think. And you overlay them on top of each other, one subtracted from the other. I did introduce a little bit of offset so at least you can see what's going on, but now you can start to adjust the positioning, the scan width, the rotation, and the linearity to get all three camera tubes registered to each other. So that's kind of a quick cover of things you do to set the scans up on a camera. Next thing, of course, now is the linearity of the signal. And there's a bunch which I'll get to in the next set of slides, but not quite sure why this one's here. But one of the things you do is you make sure that you're getting a grayscale out of it. This slide should be grey and white through black, and obviously this camera is not adjusted correctly at this time. Now I seem to have a blank slide. That particular camera has what's called auto white and auto black. Normally you tweak on controls of the red and blue to match the green. In this case, the camera can do it automatically. And after the button was pressed, that's the result it gave. Yeah, the slide I've lost was before I pressed the button, and there was a lot of chroma on the waveform monitor. On this one, you see that it only scanned one or two lines, but you see that there is some signal in there, but it's not actually chroma. The chroma's actually gone, and it really is black and white at this point. That was the test that I was running there. Incidentally, the slide box that I showed you, which had the big 8x10 slides in it, goes to great lengths to make sure there's no inherent shading in the image that you're looking at. So there's multiple layers of milk glass in there that makes it nice and even. That's it for cameras at the moment. So we'll move over to getting the signal from one place to another through whatever, processing equipment, in some cases storage equipment, and so on, getting it out to the display device. So we'll look at some test signal generators. For a long time, most people had one of these somewhere. Very often it was the master source of synchronizing signals for the station. So one of these, they're usually quite well built, and they came in various versions. There was versions that concentrated on certain types of test signals, depending on what your particular needs were. In this case, I'm showing a PAL one and an NTSC one. This particular NTSC one is the one I really needed at the time, because here there are two knobs that allow you to move the crosshatch horizontally or vertically. Because when we take that bubble chart image, we need to move something to get them all lined up. And it's much easier to get hold of these knobs and move the chart around and line it up on the bubbles. So that's one version of it. This one is kind of the same vein, same era. It's for measuring noise. So it'll generate calibrated levels of noise, which you can adjust through a bunch of attenuators over here. Or it can measure noise. So it'll actually go in there and help you measure noise. That's about all I can say about that. I don't have a lot of experience with it. It's one of those things that has a funny connector on the back, like John had on his viewfinder, and I need to make a connector. Then they went to some smaller generators. So there's two generators showed there. Once again, each generator may be designed around doing certain functions. The one on the left was really aimed at cable TV industry, in this case. The one on the right was back to regular television engineering in the studios. Then the one on the top I actually brought along today because I'll use it to show you some signals. These are... I've gained a mouse. It's like my studio in Syria. So I brought along one of these generators, the portable one. It's really convenient. It doesn't take up a lot of bench space. That's the main thing. I think you all know what I mean by needing bench space. It does PAL, it does CCAM. So that one's convenient. I also brought actually a monitor, picture, waveform, and vector scope that's very useful to go with it. And it's suffering the demo effect. It worked several times at home. I brought it here and I can't get the power connector to go in for some reason, so I won't demonstrate that. So the test signal generators, like I say, this one was really aimed at the cable business. And the one to the right was more the generic studio application type of generator. Once you've done that, you notice the earlier picture signals I showed you are on an oscilloscope, and I think most of you have probably played with television. Now it's a pain. Every time you want to look at something different, you've got to adjust the sweep rate and amplitude and re-trigger it maybe, and so on. So it's really nice to have a display device that's custom set up for television. So typical settings are horizontal, 2 horizontals, 1 or 2 fields, and sometimes you can have it select only one line, and that's very useful because once you start using vertical inserted test signals, VITs as they were known, you'd want to select only that line because the rest of it was junk as far as measurements were concerned. And it has automatic synchronization, there's no tweaking with syncs. So yeah, and earlier on, quite often, some of the monitoring facilities were built into the picture monitor that you were using in the studio, or camera control units often had them built into the camera control unit. So here's a few waveform monitors. Notice you have a nice waveform monitor downstairs, similar to this one. This one, the early generation, of course, all had round tubes in them. This is a particular well-known English make, EMI, and that one is probably from the early 60s, very early 60s. A little bit later, Tektronix produced this sort of size. And then gradually, as time went by, things got smaller, so they started to produce these small ones. These were typically, they got a reduced amount of capability, but they're often built in to, say, a camera rack or into a VTR console so that you could easily monitor the horizontal and vertical waveforms. This one's really nice. It actually is a waveform monitor, but it's also a vector scope as well. Then finally you have the one that I can't demonstrate today because it's not working. As I said, you could actually have these built into a picture monitor as well. So this is an early RCA unit. You just saw it in John's presentation earlier. So there's a typical RCA unit with the waveform monitor and the waveform controls built in there. John's not going to like the next slide. Not such great condition as his camera, but this is a TK-31 camera control unit. And came with, actually this is not the, it is the control unit, the TK-31, not the 11. The 11, you actually use that previous box I showed. So on the 31, you've got the waveform monitor built in and all the controls on the front panel there. And not just RCA, this is a PI, a British camera channel. This is pretty similar era, pretty same time as the TK-31. So same story. If you look at if you could read the controls, you'd see that for an image orthogon, 3-inch camera tube again. Monitor, picture monitor. So we need waveforms to test all this stuff out, and we saw there's multiple different generators there. So some of the generators really were aimed, like we saw with the cable television one, aimed at a certain type of sets of measurements. But and signals were aimed to do specific tasks: frequency, phase, response, because not only is bandwidth important in television, but you also want the frequency throughout that bandwidth to remain in the same phase. For example, you've all, maybe in college or wherever, you studied how a square wave is, and it's made up out of a fundamental, a third, a fifth, and etc. harmonics. If those are not in the right phase setting, it no longer looks like a square wave, even though the frequency of all those signals would be the same. So phase is very important in television. And then when we got color, of course, that brought in a whole new set of measurements, and phase of the color subcarrier is very important. Occasionally you can look at things with spectrum, from a spectrum point of view. This is a spectrum of color bars. Let me get my crib notes here, otherwise I'll forget to do things. So that's the spectrum of the color bar signal that you're seeing. And I may have cheated a little bit because I think this one is 70, this one's 100%, and this one may be 75%, but it's about the same thing. Maybe I do need this here. I've got to remember how to make this work. It's really like 50 years since I really did a lot of this stuff, so over the years I've done less and less. So there's the crosshatch that I keep mentioning. That's the pure crosshatch. That was what I used with the bubble chart, and useful for checking the linearity of a TV display itself. I don't know why that one's included in a technical generator, but that's the safe area. So that allows you, I've got to look at the right monitor, right? So that allows you to see or superimpose on a viewfinder, for example, what is the safe area. Nowadays, it's probably not that important. We have LCDs and they display everything. But in the old days, particularly some of the ones you look at around downstairs, you've got round tubes and you're going to lose stuff. So typically the scanning was brought in from the actual limits so that you could see everything. This allowed you to, and you can move these lines around on this to actually change them. Red field is nice for purity of color television displays. It's also useful in VCRs for checking certain parts of the modulation process. And plain white field, 50% white field. And hopefully, I didn't get one. 5 steps, yeah. 5 steps generates a waveform that is nice if you're setting up. Well, it's good for testing linearity of the system because each step should be the same. And a quick way to check that is to differentiate the leading edge of the steps, and they should all be the same height. So that's a quick way of testing it. Not sure that it's that great because if there's a change in frequency response for some reason, it will change it also.
Can you use it for differential phase and differential gauge?
There's a signal very similar to that, and yeah. So this one's got no color content to it, so it wasn't used for diff phase and diff gain. But the other use for it is you bring a color monitoring device or color meter or a light meter even, and you can measure the luminance on each of those and check that the monitor is set up to give the correct grayscale. And of course, multi-burst, I hope, yep. Multi-burst was a quick way of checking frequency responses. It was easy to see. That's what it should have done. That's on a spectrum analyzer. The marker is at color subcarrier, so that's not a burst actually that you're looking at. It's the subcarrier coming through. There's still lots of subcarrier in this image on the burst. Now we get to the more complicated signals, and we start putting lots of things together in one picture. So in this case, we can, I don't have a display of my own. I was relying on my little box to display for me. So we've got the pulse, the bar rather, they call that the bar. So there was a certain test called pulse and bar, and you monitored the bar and this pulse here, which is a 2T pulse, and it's got a particular shape such that it has high frequencies in it, but they tailor off as you get towards the bandwidth of a TV system. And it was convenient you got all those together, and then you got this modulated pulse. That's actually another pulse. It's called a 10T pulse in this case. It's another pulse, but it's got a modulated carrier of the same envelope, and the two should match. And I think I've got slides to show that a little further in. And then something with color on it in this case. This is a graticule actually for looking at the pulse. And I don't know whether it was super popular in this country or not, but in the BBC they use this a lot. So they'd look at this pulse. Yes, over here too.
I used to see this on satellite broadcasts.
Okay.
It's definitely an NTSC and until
okay, yeah. I know that this is NTSC generators make it, so I assume they did. But generally what they did is they'd have this graticule, and if the distortions of that pulse, there's very little distortion here, but there's a little bit of distortion there, but not enough to reach the first line below it, which is a 1K, I think it was. And then the next one out, maybe it was 5K and 10K, I can't remember now. But they were K ratings, actually. This would help. Maybe not. There were instruments that were set up that would automatically go in there and measure. You didn't even have to look at a graticule. It would actually measure the pulse and read out on a display. There's another Tektronix wonder. It's a VM700. I never really worked with them much myself. There were one company I worked for, the one that did DirecTV. On the manufacturing floor, the operators and people who were getting the gear working, they didn't really know how to run vectorscopes, K graticules and so on. So they used VM700s a lot. And you had it pre-programmed to measure certain things. I never fell in love with them though. But you had to spend a lot of time programming them to measure the right things. So the next one, chroma luminance, and everything else sort of all in one go. Can't read this. Yeah, I did get it. That's what I wanted actually. And here we see what I was discussing earlier was this modulated 10T pulse What it's composed of is there's a luminance component, which is only 50% amplitude, and then there's this modulated envelope at subcarrier frequency. And if you superimpose those two, because this is plus or minus half of amplitude, you should get a nice flat bottom. Now, if the chroma amplitude is going through the system with too much gain, then the bottom would stick down. So the amplitude would be too much to match the exact height of the pulse. If the phase of the chrominance is wrong, the chroma will move with respect to the pulse that it's sitting on. So it would give a quick indication of gain and phase of the subcarrier system.
Actually, you're talking about group delay. With a modulated 12.5 response, you're talking about group delay. And Tektronix provided nomographs.
Yeah, I don't know, maybe they did call it that, yeah. It actually says 12.5 T pulse on there.
12.5 T.
Yeah.
Tektronix provided nomographs showing the distortion of the baseline that you could read off in group delay.
Okay. And hopefully you're seeing one of those kind of displays there. So I really did need that, didn't I? So there we're seeing the bottom of that pulse, and the chroma should be exactly the same amplitude, and it looks like it's a little high on this one. The chroma is going down below the baseline. Also, if it's still displaying the same as at home, it's a little advanced. You'd expect it to be really close because all I'm doing is going from the generator to this measurement box. This measurement box is one of the display devices I showed you. I can use it as a display, or I can use it as a vectorscope or a waveform monitor. It's quite a useful thing from that point of view. Back to a picture. The next slide. I inserted a few slides at the last minute. I found some nice pictures in books. So there is one where the chroma is rather late, and you see that the chroma is shifted over to the right because of delay in the chroma signal. And from that point of view, you see the chroma delay. You can also do differential gain as well. So here we're seeing this should be nice and flat. Each of those bursts of RF on the rising steps, even though it's either at a low level or a high level, the amplitude of the subcarrier should be the same. In some of these test equipments, the waveform monitor could actually see subcarrier phase and gain. So this is an example of a Tektronix 1780, somewhat similar to one of those I showed. And it's looking at the phase of subcarrier on each of those rising steps. And we can see that obviously there is a change in subcarrier phase in this case. So yeah, differential phase. From a cable generator, you would be able to get this sweep. This has a timeout on it, and if I don't step around in time, it locks itself out.
You had it. It went back.
Did I have it?
There it is. Oh, no. Yep.
There we go, yep. So cable sweep, And that's the spectrum that you see there. It goes out a little further, it's out to 4 megahertz, nice and flat. Probably should have mentioned earlier on, we'll get to it in a minute, we are, there we go again. So we do have, well, we're not really there. This is hard to, Yeah, unfortunately it's not on that one. But there is another signal which I seem to have lost, which is called sin X upon X, and it's a very clever little signal, and it's for testing frequency response of amplifiers. And that's what this is, a spectrum of sin X upon X. The hump, of course, is the burst, the subcarrier burst coming through again. But you notice how nice and flat it is, and it looks rather like that 2T pulse that we looked at before. It's a little different. There's some, I don't seem to be able to find it in there anymore for some reason. Should have been right after the cable sweep. There it is. So these two pulses here are sin X upon X, they're called, and they have a very fast rise time and short fall time, but if you look at them on a waveform monitor, they have some ringing on them, and they produce this very nice flat spectrum, so they're convenient for doing quick tests without messing with looking at amplitudes of different frequencies. Then we get to, as things got better and transistor equipment got smaller, you could do a lot more with the waveform monitors, and you could easily go to a specific line or two and measure just that line. So instead of messing around jumping from one generator to another, they were able to incorporate them all. And I was going to show you line select, but I'll drop out of that for time consideration. But you can select which line you measure, and now you can move just at the waveform monitor. You can move from one test signal to another and not be changing the settings on the generator itself. Not a very interesting one. It's like and no burst. Field square wave. We also, it's not just high frequencies in television, it's low frequencies too. So this should look good, you know, it shouldn't be shading towards the bottom because you've got a CR network type of effect going on. So a field square wave was good for just checking that sort of thing. And finally, final one in those is what's called a bounce signal. And it checks the very low frequency response, whether all the capacitive coupling is good. And the signal should not be bouncing up and down. The clamps should be clamping the black level of the video perfectly on every line. So finally, let's move to outputs. So now we've tested the input, getting it to the output device. Now we want to actually see what we're looking at. And we still need to check the scanning again, size, linearity, and the registration in the later color sets. And same with color amplitude. We're still looking at blacks, whites, the gamma, the color, and the linearity of the color. In the early days, we had test cards. And it was annoying. This is the test card I grew up with. You know, when I first went to the BBC, I think they were still using it. And it tests a lot of things in there. There are frequency sweeps and grayscales and kind of a thing for checking linearity, although the circle was always a good indicator. Things so that you could see where the edges of the picture were, stigmatism tests, low frequency testing, high frequency pulse response, so it was quite convenient. One of the things I didn't show you in the input devices is one of the things for generating a test signal was using a monoscope tube. Basically, it was like I can't remember whether it was a 5-inch or a 7-inch. I think it was a 5-inch. Yeah, and a 5-inch tube, but instead of having a photosensitive target, it actually had a piece of metal with a test card printed on it. And so we scanned this piece of metal and it generated an image, and you know that the image was correct and you didn't go through all the tribulations of getting people out of the way or any of that stuff. The only trouble is it's kind of like the TK-31. It's a rack unit about that high, and then there's another rack unit about that high to generate enough high voltage at hundreds and hundreds of milliamps at 450 or something like that. It's a monster of a power supply and piece of equipment. Of course, in America, you guys are much more familiar with this one, if you're into antique television images. So we had what was called the Indian head test card. And then later on, I joined the BBC about a year or two before they put colour on the air. So I grew up, like I say, with the test card C, and shortly later we had the test card F as we introduced colour. So a lot of the same things, frequency. This time, the actual grayscale, if you could see it, there's a slightly different colour grey in that black box, and a slightly different level in the white box. And that was to ensure you looked for those, because that would tell you you're not crushing it. You haven't set the brightness down so far that you're crushing the image. And some of the signals that are different to black and white, these little blocks of colour here, were to make sure that you weren't, the burst sampling wasn't offset somewhere wrong. Actually, probably these did more of a, because they're the red and blue, they were closer to the burst. So those checked to make sure you weren't sampling in the wrong place with the burst. In the TV studio itself, things got a little more critical than just looking at the test card. You actually, there were two stages. You know, you could go through the stage where we use the eyeballs. Not everybody's eyeballs are very good, so there's also measure with instruments. But mostly in the TV studio, before you start a program, you would select a signal which was called plugge. BBC named a lot of things with these names, and plugge actually came from because it's a picture lineup generating equipment. Plugge. There was another one that I remember, not relevant today, but it was called Tariff, and it was Tony's apparatus for rectification of indifferent film. So that was called Tariff. They had a lot of those sort of things. So this one, plugge, you had the grayscale, which you could go in with a meter and actually check that the levels were correct. And then you had these two here, which the whole picture is a little bit brighter on this slide. But the idea was that you set the contrast, the black level of the monitor, such that you could not actually see these two. The black one disappeared into the image. There's 2% difference between that, and that. So this one you should be able to see. So that set the black level quite accurately. But the white level, usually the guy down on the studio floor had a light meter, and he just went and checked each one with a light meter. In the industry, you probably got a little bit more sophisticated, and you did use a meter for everything. So this is indication of me using a meter to check, in this case I'm checking white. So as you see up there, it measures it in this. It has multiple settings. It's good for setting up colour monitors, which you can do red, green, blue, and see the percentages. But in this case, it's reading out colour temperature. So top line says that's got a colour temperature 5,230 degrees Kelvin. There's no delta V, no delta Y, and that is the actual level, I think, of the luminance in this case. It's kind of rushed through, but hopefully it kind of opened your mind to some of the other test measurements you could make. A really good reference, it was my Bible when I was in the industry, was this book here. This one's a later one, reduced. This one's kind of about that thick. The bottom one is about that thick, and it's all on television measurements. It was probably written in the monochrome era. Weaver, originally he worked for the BBC, and he was part of our research department, and he came up with all this sort of stuff. BBC had a research department where they all had PhDs, and they really looked into things. Another good reference, which is easier for you guys to get to, is one by Tektronix, NTSC video measurements. And I assume you can get to this presentation later anyhow. And there is the web address for that. Well, that was kind of rushed through. Like I say, you really spent about a week learning all this stuff. But hopefully that got me through in my 45 minutes or whatever. And any questions?
We've got time for one question.
One question.
If anybody has
any question. Not questions.
Otherwise, there's lunchtime in the afternoon yet to chat with Kevin as you see fit on all kinds of detailed questions. I've got a few stored up for later.
Okay, thank you for your attention. Thanks.
The girl on the BBC test card F, she was interviewed probably 20 years ago, 10 years ago, and she's an older lady, and she showed her doll, the little kind of stuffed animal that she had with her, and they gave a whole background about how she was picked out of some grade school.
I think she was the daughter of one of the. I think she was the daughter of one of the engineers, or in the BBC.